of geometrical isomers. Okay, so for example, if they had given any polyenes, what is meant by the polyene, Anjan? Polyene is nothing but if the compound is containing more than one double bond. Okay, if the compound is containing more than one double bond. Okay, so when it is having more than one double bond, how we can calculate the total number of geometrical isomers? Okay, so here we have a shortcut. So what is the shortcut we are using? Means here we have a formula to calculate the total number of geometrical isomers. Okay, so what is the formula we are using to calculate the total number of geometrical isomers? Sometimes to calculate the total number of geometrical isomers. Total number of geometrical isomers. So how we can calculate the total number of geometrical isomers? Means we have a two formulas. Okay, so we have a two formulas. So what are the formulas? Means first of all, so both the terminals, that means so this side corner and this side corner. Okay, so both the corners we have to check it out here. If the terminals are having same atoms or group of atoms, the condition here. So what is the condition? Means here first condition is, okay, if terminals are terminals. So terminals means both ends here. Okay, so terminals means here both ends. If the terminals are not same, okay, terminals are not same. Okay, so if it is not containing same atoms or group of atoms, then the total number of geometrical isomers is equal to, then the total number of geometrical isomers, total number of geometrical isomers is equal to 2 to the power of n. So what is the formula we are using to calculate the total number of geometrical? Means here 2 to the power of n. In this one, n is equal to number of double bonds. N is equal to number of double bonds. Number of double bonds. Okay, so we'll see one example. So what is the example? Means, for example, if they had given like this, that means CH3 bond CH, double bond CH, double bond CH, double bond CH bond C2H5, it is that. So this is the example they had given. Okay, the given compound. If the given compound is exhibits the total number of geometrical isomers, okay, or the total number of geometrical isomers are exhibited by the given compound. How we can calculate, Anjan? First of
So it
all,
is 2 to the power 2, sir.
very good, Anjan. So how you are taking, why you are taking as a 2 to the power of 2 means here, this two terminal, this is the one corner and this is the one corner. So one corner is attached with the methyl group, another one is attached with the ethyl group. So terminals are not same. Terminals are not same. If the terminals are not same, means what is the formula we can use? Means 2 to the power of n. In this one, what is the n value? In this, what is the n value? Means n is equal to 2. Then what is the formula to calculate the total number of geometrical isomers? Total number of geometrical isomers. Total number of geometrical isomers is equal to 2 to the power of 2. So what is the 2 square value? Means 4. And the total number of geometrical isomers is equal to 4 you will get. So now you got the clarity, and John?
Yes, sir. What if the terminals are same?
So that is only I'm going through the next condition. Okay, so what is the condition? What is the next condition? Means here, if terminals are same, if terminals are same, if terminals are same, if the terminals are same means, okay, here also we have two condition. Okay, so what are the two condition means here? So in the case one, what is the first case? So what is the first case? Means here, first of all, condition is the terminals are same, and if the compound is having, the compound is having equal number of even number of, it's not the equal number here, it is even number. Okay, it is having here. So if the compound is having even number, okay, even number of double bonds, even number of double bonds. While having the even number of double bonds, the total number of geometrical isomers is equal to 2 to the power of n minus 1 plus 2 to the power of n by 2 minus 1 is the formula. So by using this formula, we are going to calculate the total number of geometrical isomers. Okay, and what is the another condition? Condition is same. If the terminals are same, and what is the case 2? What is the case 2 means here? If the terminals are, no, sir. Okay, if the compound is having odd number of double bonds. Okay, if the compound is having odd number of double bonds. The compound is having odd number of double bonds. The compound is having odd number of double bonds. If it is having odd number of double bonds, means what is the formula we can use? We can write means here 2 to the power of n minus 1 plus 2 to the power of n minus 1 by 2. It has a small difference. Okay, it has a small difference. Shall we see here how we can calculate? We can see the two examples for these conditions. Okay, the first example. First, I am giving one example. What is the example means here? CH3 bond, CH double bond, CH bond, CH double bond, CH bond, CH3. Okay. Now, so can you calculate the total number of geometrical isomers for the given compound? The total number of geometrical isomers for the given compound. How much will you get?
2 to the power of 2 minus 1.
2 to the power of 2 minus. Which formula, Nana? First of all, let us see.
With case 2, sir.
Terminals are
Sorry,
same. Case 1
even.
or case 2 formula?
Case 2, sir.
Case
No,
2
no,
or
no.
case 1?
Case 1. Even.
Even number of double bonds are there. First, we have to check it out the number of double bonds. If you see means we have a 2 double bonds. 2 is the even number. While having the even number of double bonds means we can use the formula is 2 to the power of n minus 1 plus 2 to the power of n by 2 minus 1 in this one. So 2 power n. Okay, so 2 power n. What is the 2 power n? 2 n value is equal to 2.
Answer,
So
answer is 3, sir.
answer is 3, ma. Very good, ma. Okay, answer is 3. So 2 power 2 by 2 minus 1. 2 by 2 minus 1 means you will get as a 2 power 1 and 2 power 0. So what is the 2 power 0 value? 2 power 0 value will get as a 2 only,
1.
na? And 2 plus 1, sorry, 2 plus 1. The total number of geometrical isomers is equal to 3. Okay, and I'll give one more example. So what is another example means here? For example, what happened today? You only CH3 bond, CH double bond, CH bond, CH double bond, CH bond, CH double bond, CH bond, CH3. So this is the compound they had given. Okay, so this is the compound they had given. And then, so the total number of geometrical isomers in a given compound.
Okay. It is odd number, so 2 to the
Okay,
power n minus 1.
very good, ma'am. So what is the
When
formula? This means first of all, terminals are same and the compound is having the odd number of double bonds. While having the odd number of double bonds, the formula is 2 power n minus 1 plus 2 power n minus 1 by 2. Okay, in this one, 2 power 2 3 minus 1. 3
yes,
minus 1.
10. Answer is 10, sir.
Approximate. Okay, ma'am. Shall we see here? So 2 power 3 minus 1 by 2. So 3 minus 1 by 2 here, 2 power 2 you'll get.
No, sir, it
Here
is 4 plus, okay, 4 plus 2. 6.
6. That is only. So 2 power 2 by 2. So 2 by 2 value how much you'll get? 1 only. Na? So according to that one, 2 square value is equal to 4. 4 plus 2. The total number of geometrical isomers is equal to 6. Okay. So when we can use this formula means only in Paulins. Only in Paulins we can use this formula. Okay. So Paulins is nothing but the compounds which contains more than one double bond is called as a Paulins. Now you got the clarity, Anjar? Okay.
Yes, sir.
So then we'll go for the next one here. Okay, in this one only, some other examples are there for the geometrical isomers. So what are the other geometrical isomers are there for us means here? So one is syn and anti. What is the another geometrical isomer means here? Syn and anti-isomers. Okay, so which compounds are they exhibit as a syn and anti-isomers means here? Azo compounds and oximes. Azo compounds and oximes are they exhibit as a syn and anti-isomers. Sir, which we can call as a azo compounds means here the compounds which contains N double bond N. So this we can write as general formula of the azo compounds is R N double bond N are called as a azo compounds. Now let us see. In this one, syn is nothing but same side of the double bond. Okay. Now first we can check it out here. If I am writing as some structure, for example, N double bond N here. So each nitrogen atom is having the one lone pair of electrons. Okay. So each nitrogen atom is having one lone pair of electron. If two alkyl groups R is nothing but it may be alkyl group or aryl group. Now here and one more structure I am writing N double bond N. Here R. Here R. So this one and this one. Now let us see. In the azo compound, these two are the examples of the azo compounds, which we can call as azo compounds means here N double bond N compounds. In N double bond N compounds, each nitrogen atom is having the lone pair of electrons. How many lone pair of electrons are there? One lone pair of electron. Now, which one we can consider as a syn and which one we consider it as an anti means based on the lone pair of electron. If the lone pair of electrons are present same side of the double bond means that we can call as a syn. If the lone pair of electrons are present opposite side of the double bond means that we can call as a anti. Okay, now you got the clarity, Anjan. Based on lone pair of electrons, if the lone pair of electrons are present at same side of the double bond is called as a syn. If the lone pair of electrons are present at opposite side of the double bond with that we can call as a anti. Now you got the clarity. Now I'm going to write as one example. So one example I'll write here. So this we can write as a C6H6 azobenzene H5 H5 bond N double bond and here we have one lone pair and here also we are having one lone pair and this side one more C6H5 and one more structure I'm writing N double bond N. So this one is having C6H5 opposite side C6H5. So which one is syn and which one is the anti, Anjan?
First one is the syn.
Okay, first one is the syn.
Second one is the anti.
Second one is the anti. On which basis you are explaining the syn and anti?
Because C6H5 and C6H5 are on the same side,
Okay,
and the lone pairs are on the same side. And for anti, C6H5 and C6H5 are opposite sides towards each other,
okay.
and it's also opposite side towards each
Opposite. So two lone pair of electrons are present in opposite side. Generally one we can take. Sometimes what happens they can give two different alkyl groups. So now I had given identical. Okay. Now I had given identical. That's why we're telling that identical atoms are group of atoms present at same side means that we can call as a syn. Identical atoms are group of atoms are present at opposite side means that we can call as a trans. Okay, if I change the alkyl group means on which basis we can explain means based on the lone pair of electrons. Now you got Tanja? Got it?
Yes, sir.
Next, oxime Sanja. Oximes. Okay, so which we can, what is the general formula of the oximes means R CH double bond and bond OH is called as a oxime. Okay, so in this one, syn and anti, which on which basis we are going to be explaining means based on H and OH groups. Okay, so based on H and OH groups, we are going to be explain the syn and anti. Okay, if the H and OH groups are present at same side of the double bond is called as a syn. If H and OH are present at opposite side of the double bond is called as an anti. Okay, so if H OH groups are present at same side of the double bond is called as a syn. If the H and OH groups are present at opposite side is called as an anti. Now I am going to write as a some structures. So C double bond N. In this one, here H it is there. Here CH3 it is there, and this side OH. And on nitrogen atom we have one lone pair of electron. Okay, and one more structure I am writing. C double bond N bond CH3, and this side OH, and this one is having one lone pair, and this we are having H. And then which one is the syn and which one is the anti?
Sir, first one is the sin.
Okay, very good. First
Second
one
one is the
is
anti.
very good, Anja. First one is the syn and second one is the anti. First one is the syn, second one is anti. So now you got the clarity. Okay, until here.
Yes, sir.
Okay, so this is about here complete geometrical isomerism. Okay, next we will go for optical isomerism. What is the next important concept means here? Optical isomerism. Optical isomerism is there in 12th standard, na? Where you are getting as optical isomerism?
11th also, like we studied like basics, like 11th.
Where you studied 11th? It is a main concept in 12th actually. It is a main concept in 12th. Okay, or where you are studying about the optical isomerism means in haloalkenes, haloarenes. Did you remember?
Yes, sir.
Okay, so there you will get this one. Optical isomerism. So actually this is the basic information. So next upcoming organic chemistry, I don't want to discuss about the isomerism. Okay, so directly just we'll discuss about the preparation and properties. That's why I'm going very slowly. And then don't know what happened to others. They didn't join. They didn't join. Actually, this is an important concept to us. Okay, so let them leave. Right now, let's see. So we are talking about the optical isomerism. Okay, here. So before going to the optical isomerism, first we have to know some terms. What are the terms we have to know means here? So first term is optical activity. Okay, optically active compound. Optical active. Optical optically active compound. Optically active compound. Okay, so which compounds are the exhibit as optical isomerism means here? Optically active compounds are the exhibit as optical isomerism. Simple statement. Okay, so what is the optical isomerism means here? Which compounds are the exhibit as optical isomerism is optically active compounds are the exhibit as a optical isomerism. Okay, so first of all, what is meant by the optical activity? Okay, so which we can call as optically active compound means here the compounds which contains chiral carbon or asymmetric carbon. Okay, the compounds which contains chiral carbon or asymmetric carbons are called as a optically active compounds. Okay, what is the definition we can write for the optically active compounds? Means the compounds which contains so chiral or asymmetric carbon, chiral or asymmetric carbons. Okay, so the compounds which contains chiral or asymmetric carbons are optically active. Half of the chapter it is the optical isomerism in haloalkanes, haloarenes, SN1 reaction and at all stereochemistry, what is the stereochemistry of the SN1 reaction and what is the stereochemistry of the SN2 reaction at all. Okay, optically active compound. Okay, right. So in this one, first of all, what is meant by the chiral? Do you have any idea about the answer? What is meant by the chiral?
Sir, I
Okay.
have studied, but I forgot, sir.
Okay. So here, chiral is nothing but actually uh, in Kannada and Tamil, kai is nothing but hand. Anjan. Okay. So in Kannada or Tamil words here, kai is nothing but hand. So can I ask one question, Anjan? And then if you observe your hand is having same size of the fingers or different size of the fingers.
Different size of the fingers.
Different size of the fingers. Okay, so different size of the fingers we are having our hand. Okay, now here also what we can say means chiral carbon, which we can call as a chiral carbon or asymmetric carbon means the carbon which is attached with the four different atoms or group of atoms is called as a chiral carbon. Okay, so what is meant by the chiral here? Like our hand. However, the hand is attaches with the five different sizes means. Similarly, here also the carbon which is attaches with the four different atoms or group of atoms is called as a chiral carbon. A, B, C. Okay, so this carbon is called as a chiral carbon. And this is also we are calling as a asymmetric. Why we are calling as a asymmetric means here, if you divide in any direction, if you check it out our hand, if you divide in any direction, and is any possibility is that to get as a two equal halves? Anjan?
Sir, I didn't get it, sir.
Okay. So once again I'm asking the question. Anjan, my question is our hand is there. If you divide in any direction, are you getting as a two equal halves? If you
No,
cut,
sir.
I'm asking to cut our hand. If you cut our hand in any directions, is any possibility is that to get as a two equal halves?
No, sir.
Is not possible because of size is different. Let us see if you cut like this means your this size finger size it will be different. Okay. Otherwise, if you cut like this means fingers are coming out at one side and palm is coming at one side here. Okay. So if you cut any direction, you won't get as a two equal halves. Whenever you are getting as a two equal halves means that we can call as a symmetry. Okay, so whenever you're getting as a two equal halves means here that we can call as a symmetry. Okay, now whatever the compound I wrote here, so there is a symmetric or asymmetric?
Asymmetric, sir.
Asymmetric. If you won't get as a equal halves means that we can call as a asymmetric. So chiral or asymmetric means the carbon which is attaches with the four different atoms or group of atoms is called as a chiral or asymmetry. Okay, those compounds are optically active. Now you got the clarity. Okay, sometimes they're asking the questions. Okay, sometimes they're asking the questions based on alphabets and John. Okay, based on alphabets. Okay, so based on alphabets. So on which means here, for example, here they had given as a capital A. Is capital A is optically active or optically inactive?
So, I mean, is it symmetric or like is it unsymmetric?
Okay. So anyway, any direction, if you cut means if you are getting as equal halves means it is
Same,
unsymmetric
same.
only. It is optically inactive only.
Okay, it's optically active, sir.
Optically active or optically inactive?
Like if we cut vertically, then
I'm
both
not
halves are
talking about the
symmetric.
vertically. Any direction you can cut. My question is any direction you can cut.
Okay, any direction it's not there.
Okay.
Okay, sir.
Ma,
Any direction it's not.
it,
It's not
it is
optically inactive.
my question is optically active or optically inactive. That is my question.
In every direction, okay, sir. It's not symmetric. It's asymmetric.
It is a symmetry. Ma. Let us say, sir, how you are telling that it is a symmetry means if you cut straight manner vertically. If you cut vertically means you are getting as a two equal halves.
Yes,
Okay.
that's
If
what,
you
sir.
cut
I'm saying.
so if you cut vertically means it is having the two equal halves, then it becomes as a optically inactive. Optically inactive. It's not the optically active. It does not exhibit as a capital A, is does not exhibit as a optical isomerism. And one more question I'm asking here. So O, capital O, is optically active or optically inactive?
Optically inactive.
Optically inactive. Because of if you cut any direction means two will get as a two equal half. If you get as a two equal half means that it becomes as a optically inactive. Okay. And one more my question here. So what is another question means here? And here what is another one means here? Capital B. Is B is optically active or optically inactive?
Optically inactive.
Optically inactive. So because of it has a plane of symmetry. Okay. So if you cut middle means you will get as a two equal halves. If you got as a two equal halves means that we can call as a optically inactive. Okay. Optically inactive. Okay. Then P, capital P.
Optically active.
Very good one. Optically active. Optically active. Okay. So like that based on alphabet, sometimes they're asking the questions. Okay. If you see means especially our college examinations and all be based on this one also sometimes they're asking the questions here. Okay. So now you got the clarity now how to find out the optical activity and at all optically active and optically inactive. Is that clear?
They're asking in the mains.
They're asking the mains. Okay.
I wish I could get in final paper.
Huh?
I
Anjad,
mean,
come on.
is it in PYQ, sir? Previous year's questions.
Previous year's questions, once you solve, you'll get some idea. So which book you're following to get some idea?
Arihan, sir.
Arihan, very good. So in that one, some questions are there. So based on this one related to this concept, today we are going to discuss about the optical isomerism. After finishing this one, just to go through that one. Okay?
Okay.
Yeah?
Okay.
Right, sir. Okay, so this is the chiral center. So next, what is meant by the so plane polarized light? This is the one term so which we have to know here, and I'm calling as a plane polarized light. Plane polarized light. So which we can call as a plane polarized light. What is meant the plane polarized light? So plane polarized light is actually you may got as a light chapter in physics. Is that clear, Anjan?
Yes, sir.
Is light is travels in all the direction, otherwise it travels only in one direction.
All the directions.
Very good. Okay, let us see, sir. If the normal light we are taking, so light is travels in all the directions. Okay, so generally light is travels in all the direction. That we can call as a normal light. Okay, so when the normal light is passes through the prism, okay, let's consider it as a prism through the prism. So which is made up of, okay, so which is made up of nickel. So this we can call as a nickel prism. Okay, so which is made up of calcite, which is made up of here calcite. So what is meant by the calcite here? Calcite is nothing but calcium carbonate. Okay, so we are passing normal light through the nickel prism. Okay, so normal light is passes through the nickel prism. Okay, which is made up of the calcite. So what is meant by the calcite? Means calcite is nothing but calcium carbonate. Okay, so the prism is converts the light in a single direction. Okay, so after passing the light through the prism, light is travels only in one direction. The light which moves only in one direction is called as a plane polarized light. Okay, the light which travels only in one direction is called as a plane polarized light. So this is about the basic information of the optical isomerism. Okay, now mainly we are going to enter about here. So optical isomerism. Sir, what is meant by the optical isomerism means here? Sir, optical isomerism is completely experimental based. Optical isomerism is here. So it is completely experimental. Experimental based. It's not the theoretical based. Okay, optical isomerism is completely experimental based. So what is the instrument we are using to find out the optical isomers? Isomers means here polarimeter. Okay, we are using as a polarimeter. So we are using as a polarimeter. It is the name of the instrument. What is the name of the instrument we are using to find out the optical isomers means here? We are using as a polarimeter. Okay. Next, sir, what is mean by the optical isomerism means here? Sir, when the plane polarized light. So I'm taking as a some polarimeter. It is the instrument. Okay. So instrument we are taking here. In this one, we are taking as a polarimeter tube. In polarimeter tube, we are taking as an aqueous solution of. We are taking as here aqueous solution of optically active compound. We are taking as a optically active compound. Okay. So when the plane polarized light is passes through the optic, so plane polarized light is passes through the polarimeter tube, which contains the aqueous solution of the optically active compound. Okay, the optically active compound rotates the plane polarized light either the direction. Okay, so what is the direction is if it is rotates the clockwise direction. If it is rotates here, clockwise direction, and that is also we can call as if the light is rotates towards the right hand side. If it is rotates towards to the right hand side, with that we can call as a dextro-rotatory. Dextro-rotatory. Okay, so dextro-rotatory can be represented with small d, and this is also represented with the positive sign. This is also we can represent with the positive sign. And when the optically active compounds are rotates the plane polarized light in left hand side, so that is only we can call as an anti-clockwise direction. So whenever it rotates the anti-clockwise direction or left hand side, means that we can call as a levorotatory. Levorotatory. Okay, so levorotatory can be represented with small l, or it can be represented with negative sign also. Okay, so levorotatory can be represented with here small l or negative sign. So these two are we can call as a optical isomers, and the phenomenon is called as a optical isomerism. Now we got the clarity, Anja. What is meant by the optical isomerism means here? So when